So, law of partial pressures is easy in concept, but it's difficult to do in practice. It's hard to do when you're actually in the moment, so doing problems. So, like usual, let's do some together. I'm going to do a lot of them. Number 1 says, if I place 3 moles of nitrogen and 4 moles of oxygen in a 35-liter container. So you're taking them, you're putting them together in the same container. Those are your 2 gases. And it's at a temperature of 25 degrees Celsius. What will be the pressure in pascals of the resulting mixture? That stinks, but what are you going to do? So we'll deal with that later, the pascals part. So what we have to realize in this particular problem is we are trying to solve the P total, and that P total is the pressure of the nitrogen gas, the N2, plus the pressure of the O2 gas, right? So what I got to do is solve for each of them. Well, the pressure of the N2, well, we have a pressure, we have a volume, we have a temperature. We can use the Puvner equation. So what we do is we say, okay, we're going to set one up first for nitrogen. The pressure of nitrogen times 35.0 liters equals 3.00 moles times 0.08205 liters ATMs per mole Kelvin, right? Liters can't matches liters, moles can't matches moles. Kelvin is going to have to match here, so therefore this is 298.15 Kelvin. 3 sig figs, 3 sig figs, 4 sig figs, 5. So my pressure of my N2 with 3 significant figures is, I think it's 2.10, yeah. 2.10. Now when you're looking for a label, well, the pressure's in ATMs. That's why it's a problem for us later on, because I want the final answer in pascals. Ugh. But we'll deal with that in a minute. So pressure of the O2 now, times 35.0 liters. It's in the same container. There are 4 moles of oxygen. It's told you in the problem. Times 0.08205 liters ATMs per mole Kelvin. And we're still 298.15 Kelvin, right? Do the math on this, and you get the pressure of the oxygen to be, I believe it's 2.80. Yep, 2.80 ATMs. So P total is equal to the 2 things added together, right? 2.10 plus 2.80 for a total of 4.90 ATMs. Here's the problem. I don't want it in ATMs. I want it in pascals. So we got to convert it. 4.90 ATMs. You go look at the front page of your packet, right, for that chart. And you find 101 kilopascals in an ATM. So 1.00 ATMs, 101 kilopascals. Anytime I see kilo, I think 1,000. So there are 1,000 regular little pascals and 1 kilopascal. ATMs cancels. Kilopascals cancels, leaving me pascals, which is what I want. You do the math on that, and you get, I think it's 494,900. 494,900 pascals. Now, if you're doing this problem on a test, and you were happen to circle this one, and you missed significant figures, I wouldn't hate you for it, okay? I'd be like, you know, I'd probably give you, like, if this problem was worth 10 points, I'd give you 9 of them. Okay, you're going to do real well. But if you're a hardcore significant figures person, you would say, okay, 3 significant figures, 3 in the answer, therefore 495,000, no decimal place, pascals. And that would be the 10-point answer, that would be like the 9-point answer. But you would still do well. And that's question number 1. Okay? All right, let's take a look now at question number 2. Like I said, I want to do a few of these with you, because I think that they're difficult. Law of partial pressures is a challenging one. All right, number 2. Number 2 is a Boyle's law problem. It says you have 2 flasks that are connected with a stopcock. So let's say you have 2 flasks. Okay, and they're connected And one of them is 5 liters, the other one's 8. So we'll make this one the 8.00 liters since I made it a little bigger. And this one's 5.00 liters, right? And we say, okay, in this one, initially, the pressure is 0.750 atms. And in the other one, the pressure is 1.25 atms. Then we take the stopcock that's in the middle of this, and we open it up so that the gas in here can move into this container, and the gas in this container can move over here. So now our total volume is 13.00 liters. Well, this just becomes Boyle's law, and here's what you do. The nitrogen, I believe, let's see, the nitrogen is in this one, and the oxygen is in this one. But when you open that up, they're going to start to mix. So here's how we do it. We have Boyle's law. Initially, the pressure is 0.750 atms in for the nitrogen. And initially, it's in a 5-liter container, right? It's initially in here. You open this up, now the volume can be 13.00 liters. Well, therefore, what is the pressure? You do the math on this, and you get P equals 3 sig figs, 3 sig figs, 4 sig figs. Your answer can have 3. So I get 0.288 atms. Now, continuing along. 1.25 atms times 8.00 liters equals. Now, what's going to be the pressure when you open this up and allow these to go to 13 liters? Well, you get P equals 3 sig figs, 3 sig figs, 4 sig figs. Your answer can have 3. I get 0.769 atms. Last thing is, it says, what will be the pressure of the resulting mixture? So you take 0.288 plus 0.769. The 0.288 came from there, 0.769 comes from here because we add them together. You do that, and this was tens place, hundreds place, thousands place, tens place, hundreds place, thousands place. We're adding, so our answer goes to the thousandths place. Therefore, the final answer is 1.057 atms. That's number 2. Number 3. Number 3 involves something that is commonly called or known as a mole fraction. You have to calculate how much of something else. And here's what I mean by that. You're told what's the partial pressure of carbon dioxide in a container holding 5 moles of carbon dioxide, 3 moles of nitrogen, and 1 mole of hydrogen, and has a total pressure of 1.05 atms. And it just wants the partial pressure of the carbon dioxide. So you're told there's 5 moles of carbon dioxide, right? So the mole fraction is, this is how you do it. You have 5 moles, right? But you have 5 moles. You also have 3 moles, 1 more. So that's a total of 5 plus 3 plus 1, 9.00 moles total. So what does that mean? It means 5/9 of this is just carbon dioxide. And what does that equal to as a fraction? That's 0.555. Why? 3 sig figs, 3 sig figs. I made 3 sig figs. Well, if the P total is 1.05 atms, and 0.55 of it is carbon dioxide, or 55.5%, all you got to do then is take 1.05 times 0.555. You do the math on that, 3 significant figures, and the answer is, I have 0.583. Now, once it's a pressure, we started out with atms, so I should have put that there. Therefore, the answer is in atms. There's your answer. All right, let's keep going. Number 1. Number 1 down below. Number 1 says, a container holds 3 gases. Oxygen, carbon dioxide, and helium. The partial pressures are 2 atms, 3 atms, and 4 atms. Well, this is the easiest I can ever make a problem, guys. I give you the 3 pressures. 2 atms, 3 atms, and 4 atms. So guess all you have to do is add them together. 2, 3, 4 is 9.00 atms. Moving on. Question number 2. Yep, that's as easy as I can make it. A container has 2 gases, helium and argon, and 30% of it is helium. Okay. Well, that means 70% of it is argon. You are told that the P total is 4.00 atms. Well, this is just like the problem I did in number 3 above. 30% is a decimal, would be 0.30. You multiply that by 4.00 atms because 30% of this gives you your helium. So therefore the answer is 1.20 atms. And that's for helium. And then everything else is argon. You know what I would do then? 4 minus 1.2 means 2.80 atms for argon. Number 3. Number 3 says, if 60 liters of nitrogen is collected over water at 40 degrees Celsius when the atmospheric pressure is 760 millimeters, what is the partial pressure of the nitrogen? Well, the atmospheric pressure, I'm telling you the P total, and that is 760.0 millimeters of mercury. Then I furthermore tell you, okay, I have 60 liters of nitrogen, and I tell you have water, right? And I tell you furthermore, the water vapor pressure of water is 55.3. Then all you have to do, guys, is this. Take the 760.00 millimeters of mercury that you're given. You subtract the 55.3 milliliters of mercury that was for the water. And everything else is just going to be the nitrogen that's left over. Therefore, the answer is 704.7 millimeters of mercury. Just that easy, guys. I know it seems harder, but it's not. Because if you took 704.7, which is the nitrogen, the N2, and you add it in the water, partial pressure says you add them together, you get the total of 760. Number 4 is the exact same kind of thing, except you have a conversion to do. 92.5 millimeters of mercury is what I tell you for the water, but I tell you that I have 96.00 kilopascals for the P total. Womp, womp, womp. They don't match, right? So I tell you it's 96.00 kilopascals. So what I decided to do was I decided to take the 92.5 millimeters of mercury and turn it into kilopascals so I could subtract it. You could have gone the other way. You could take this, turn it into millimeters of mercury. It does not matter. So 760 millimeters of mercury in 1.00 atms. And then furthermore, in 1.00 atms, there is 101 kilopascals, right? So we do the math on that, we get 12.33 kilopascals. Well, the total is 96. The water is 12.33, leaving me just the oxygen. So 96.00 minus 12.33 gives me a final answer of 83.67 kilopascals. And that's how you do this whole page on law of partial pressures. Not an easy law, but you can do it.